Hi, I am Sukant. So, thank you for shortlisting me for the machine learning and NLP intern role at Socket. So, I have been assigned with two tasks. The first task is about to develop a fine-tuned model uh, using the Hugging Face and PyTorch libraries and incorporating the WNB for logging purposes, and also need to examine the convergence graph and report the perplexity metric in the end. So this is the Collab notebook which I used for training the fine-tuned model in the first assignment. So I've been using the Google Colab free version, which provides 15 GB of GPU RAM, and the first step done here is installing the required dependencies and then importing the libraries which are required for fine-tuning the model. This includes transformers library, PyTorch, PEFT, which is parameter efficient fine-tuning, which used to define the LoRa adapters, and from the transformers, we used to import the auto tokenizer and auto model for casual LM, which is used to define the tokenizer and getting the model from the Hugging Faces. Then loading the data set. So the data set I used here is from the Hugging Face, which is from AI Bytes Databricks Mini. So this is a pre-processed data set, so which has a text feature. In text feature, in each row, we have a pre-processed, well, a pre-processed instruction and response. So in in the source code, we can able to visualize it. So first two rows we are visualizing the data set. So there is a text a feature, and within the text feature we have a instruction and followed by the response, then another instruction followed by the response in the end. So this is the structure of data set we used here, and due to some resource limitations for training the model within the availability of GPU. We are just using the first 2000 rows from the data set. Over we can see there is nearly 10K rows available in the data set. Well, after that, we are defining the required parameters for fine-tuning the model, and this includes the LoRa parameters, bits and bytes parameters, training arguments, and SFT parameters. Well, first we go with the bits and bytes configuration. So this bits and bytes is just like loading the large model in a quantized way into our local machine. Let's say we used to load the Google Gemma 2B model from the Hugging Face. So this 2B implies that the model trained on 2 billion parameters, which is 2 billion weights and biases while training the model. And these each weights or biases are some kind of numerical values with high precision. For example, float 64. So there are 2 billion numerical values, each values in high precision, which is float 64, which is quite difficult and impossible to load within a single GPU machine or in a basic machine. So we need to quantize the each and every parameters. We need to convert the high precision into lower precision, like converting the float 64 into float 16, which is 4-bit. We need to convert the parameters into 4-bit. So which makes that instead of loading 40 GB of full model, we quantizing or compressing it into a 4 GB or 20 GB and loading it into a working machine, right? So that's about quantized uh, method, quantization method, and we loading the model using the bits and bytes configuration. Then we initializing the corresponding tokenizer using auto tokenizer. Then we are implementing the LoRa configuration. So this LoRa stands for low rank adaptation, which means instead of trying the or fine instead of fine tuning the model with full 2 billion parameters, we just freezing most of the parameters and retraining certain number of parameters, which results in training efficiency, like with the limitations with the limitations respect to our resources like GPU and RAM. Uh, we can see here that the model architecture, like there are several layers, so we need to fine tune the specific layers, q projection, k projection, v projection, and these kind of things. And we used to set up the LoRa configuration using the parameter efficient fine tuning um, library. Then we can see here that we just training 46% of parameters from the total parameters. So this results that instead of training the 2 billion parameters, we just training the 46% of 2 billion parameters. So that's the usage of low rank adaptation, LoRa configuration. Then we just here inferencing before fine tuning the model. So this is the input text and generates the output. So we can see that the output is just like a random sentence, like but it relevant to the input text. Uh, Performs quite okay, but it does not provide some meaningful sentences. So we setting the training parameters using the training arguments class from the transformers library. Then we reporting the logs to WNB. We can also set it for tensor board, but we are using here WNB, which is weights and biases. Then we are setting the parameters for supervised fine tuning trainer. So then we are passing the training arguments which specified in the above cell. Then we initializing the WNB project, or initializing the WNB run. Then we used to train the model with our trained data set, and we can see that we are running only a single epoch, and within the single epoch, the steps are increasing by 25. So this rule was specified in the above parameters definition, like, yeah, logging steps and save steps. Okay, so we can see the convergence graph here. So this is the convergence graph uh, projected in the WNB logging, and we can see that we can examine that the training loss comes with from ups and lows, and finally ranges to 2.341, and we can also visualize the gradient normalization, and the epochs are linearly increasing, and learning rate remains same. Then Uh, then we pushing the fine-tuned model into Hugging Face Hub so that we can use it in future cases. Then we are inferencing it after fine-tuning, like we are loading the fine-tuned model using parameter efficient fine-tuning algorithm, and in this case we used to fetch the base model, and well, we merging the fine-tuned adapters into the base model. So that's how it's work. So we are inferencing it, and this is one of inference test case, like what do you mean by polygon. So it gives a generic answer. A polygon is a geometric shape with 4 or more slides. This is the actual data set available for the question, like what is a polygon, and there's a brief answer for those for that example. Yeah. Then we computing the perplexity metric. So perplexity metric is used to evaluate a large language model. So in the case like how will the model predicts the future tokens based on the previous tokens, like predicting the next tokens in a sequence. Then our model reports that the perplexity value is 7.5039. So the lower the perplexity score, the model results in better predicting the next token in a sequence. So 7.5039 is a reasonable result. Due to some limitations in uh, resources, we cannot able to we are unable to train the model with a huge number of data set, but by improving these techniques we can able to improve the model performance also. So moving to the second assignment, the task is to explore the distinctions between prefix language modeling and autoregressive language modeling. Then we need to develop a prefix language model using Hugging Face and PyTorch libraries, and we need to pick a data set and need to train the model and report the perplexity metric. So okay, this is the notebook for the second assignment. So here we can see the distinctions between a prefix language modeling and autoregressive language modeling. Um, well, prefix language modeling, also known as conditional language modeling. In this approach, the model generates the next tokens or predicting the next tokens based on the prefix text we giving as a input to the model. Um, well, this kind of prefix language modeling is used in various applications like text completion tasks, dialogue generation, and language translation. By seeing the autoregressive language modeling, this language modeling technique generates the next token in a sequence based on the previous generated tokens. That's the difference between these two modeling techniques. Then like the assignment one, the same steps are followed here: installing the dependencies, importing the libraries, and for this assignment, I have been using the dataset called Aberrate English Codes. So this is the original dataset. The dataset contains 2.5k rows, which has three features, right? Quote, author, and tag. So we loading the data set and fine tuning it into a certain manner, like uh, this one. This is the Arbitrate English codes transformed after pre-processing the data set. Well, here we can see there is only one feature, and there's a number of rows like 2.5k, and in each row we have uh, the data in a uh, labeled manner, like quote, be yourself, everyone else is already taken, the author, Oscar Wilde. So this supervised uh, data set after pre-processing it. So this is the code for pre-processing, and we're pushing the data set into Hugging Face. So that's the thing here, and defining the parameters like before. We also using same Gemma model with 2 billion parameters, and setting the bits and bytes configuration, and loading the base model using auto tokenizer and bits and bytes configuration. Then we implementing the LoRa configurations, and the same 46% of trainable parameters. Here we can see that before training, we used to inference the model. We have quote, don't judge. So it needs to complete the sentence, but it produces an output which is not well and good. So we need to we need to fine tune it. So again, we loading the data set and setting the training parameters using the training arguments class, and we use to initialize the SFT, supervised fine tuning trainer. Then we initializing the WNB run. Then we training the model and starts to train, and this is the convergence graph of the second assignment, and we can examine that the training loss in the end comes to 2.186, and well, that gradient normalization also 3.3, decreasing from the starting value, so performs well in the training. And we pushing the fine-tuned model into Hugging Face. So we can see it here. So these are the models pushed into my Hugging Face right now. Then we loading the model, loading the base model and also the adapters. Then we merging the adapters with the base model. Then we start to inference, and this is the input code, like quote, always forgive your enemies. This is the actual data set, actual data in the data set, like quote, always forgive your enemies, nothing annoys them so much, author Oscar Wilde. This is the actual code. So we just giving an incomplete code, like this is the prefix now. Quote, always forgive your enemies is the prefix now, and it generates the output with the code with the completion of the sentence, which is 100% same to the original data. So this is the second inference we using here. Quote, be yourself, be yourself. Everyone else is already taken. Author Oscar Wilde. This is the actual thing, and it's also same like in the data set. So we are doing a we are computing the perplexity metric, and we used to take last 10 data from the data set for test data, and after performing the perplexity metric, it shows that the result is about 5.8047. Well, having a lower perplexity value results in better prediction in next tokens in a sequence of words. So 5.8047 is a reasonable and well good result. Yeah, that's it. I hope I have explained all the things which I have implemented, and thanks for listening to the video. Have a great day.